Hi everyone. Now we are at eigenvalues and eigenvectors, lecture number 6. So in the last lecture, lecture number 5, we have seen some properties of eigenvalues. So in today's lecture number 6, we are going to do some problems related to the properties of eigenvalues. Okay, let us start the session. Let us quickly recall the properties of eigenvalues what we discussed in the last class. So property number 1, the sum of the eigenvalues of a square matrix is the sum of the diagonal elements or simply trace of that matrix. Okay. Next, property number 2, the product of the eigenvalues of a square matrix A is nothing but its determinant. Okay. And property number 3, the eigenvalues of A and its transpose are the same. Both the eigenvalues are same. Next, property number 4, if lambda is an eigenvalue of a non-similar matrix A, then 1 over lambda is an eigenvalue of its inverse. Okay, and it's related corollary. If lambda 1, lambda 2, lambda 3 up to so on lambda n are the eigenvalues of a non-similar matrix A, that means A is of order n by n. That's what here n eigenvalues existed here because A is of order n. So what is the characteristic polynomial degree? If A is n by n, characteristic polynomial degree should be n. That's why n roots exist here. Okay. And if these are the roots of the non-singular matrix A, then what are the eigenvalues of A inverse? Simply reciprocals of old eigenvalues. 1 over lambda 1, 1 over lambda 2, up to 1 over lambda n. That's what we discussed in the last class. And property number 5, if lambda is an eigenvalue of A, then k times lambda is an eigenvalue of k times the matrix, where k is a scalar. Okay. Similarly, property number 6, if lambda is an eigenvalue of A, then lambda power k is an eigenvalue of A power k, where k is any positive integer. And it's related to corollary. If lambda 1 to lambda n are eigenvalues of A, then lambda 1 power k, lambda 2 power k, up to so on, lambda n power k. So power k are the new eigenvalues for the new matrix A power k, for k is any positive integer. Now, last property, take it exercise. I didn't discuss this in the last lecture. You try this in the same passion how I proceeded in these properties. Same proceed, definitely will get it. The property is if lambda 1 to lambda n are the eigenvalues of a non-singular matrix A. So this data is given to us. Lambda is A is a non-singular matrix and its order is n by n, and its eigenvalues also given lambda 1 to lambda n. Then we have to prove that the eigenvalues of adjoint matrix A, adjacency matrix of A, are determinant of A divided by lambda 1 and determinant of A divided by lambda 2 up to so on determinant of A by lambda n. So these are the new eigenvalues of the matrix adjacence of A. Try this, okay? Now let us do some problems related to these properties. Now, problem number 1. So find the uh, characteristic, find the eigenvalues or characteristic values or characteristic roots of A inverse. What is given? Matrix A is given to us. So based on that, we need to find eigenvalues of A inverse. So first we want what are the eigenvalues for A. Let us calculate eigenvalues for A. Then what are the eigenvalues for A inverse? Simply reciprocals. This is the one way of doing it. The second method is simply find out what is the inverse, A inverse. A already given to us, find out A inverse. Okay. Then we'll get a new matrix A inverse. Then find the eigenvalues for that new matrix A inverse. So that becomes somewhat lengthy. Okay. So by using these properties, we will save time. Okay. Now, let us proceed this. First, what do you want? Let us find the eigenvalues for this matrix A. First, eigenvalues. Eigenvalues of A first. So this I want to find first. Okay. So then what is the characteristic equation for that, for the eigenvalues of A? Simply determinant of A minus lambda I equal to 0. So this is a characteristic equation. Only this one is characteristic polynomial. If you write equal to 0, this is characteristic equation. And this characteristic equation is useful to find the eigenvalues of the corresponding matrix. Then, what is matrix A? It's a 3 by 3 matrix. So, what is that? 0, 1, 2, first row. Next, 1, 0, minus 1. Okay. And 2, minus 1, and 0. This is matrix A minus lambda times I. So what is the order of I now? 3 by 3. Why? Because A is of order 3 by 3. Okay. Yeah. So this is the characteristic equation of the given matrix A. And you solve it, you will get lambdas. Let's simplify this. Yes. First entry is minus lambda because here 0 minus lambda, right? And 1 and 2. And here 1 minus lambda minus 1. And here 2 minus 1 minus lambda. Determinant of this. Okay. Now let us expand. So minus lambda times, yeah. So these two, right? So lambda square minus 1, isn't it? Next minus 1 times minus lambda plus 2. Make sure that everything is correct. Okay, minus lambda plus 2. Next plus 2 into, yeah, 2 into what? Minus 1 plus twicely lambda is equal to 0. It's not null matrix, it is equal to 0. Why? Because this is determinant, right? We'll get a number. Yeah. Then expand this one. So minus lambda raised 3 and plus lambda raised 1 and plus lambda raised 1 minus 2 and minus 2 and plus 4 times lambda is equal to 0. Then this become minus lambda raised 3. Okay. And let us club first lambdas. So plus 6 times lambda, isn't it? And minus 4 equal to 0. So this is called characteristic equation of the given matrix. Okay. This is characteristic equation. So if you solve this characteristic equation, you will get the eigenvalues. Okay. Now let's solve this characteristic equation. So total here it is cubic equation. So 3 roots exist. The 3 roots are nothing but lambda 1, lambda 2, lambda 3, and those are eigenvalues. Now let us simplify this. So we get lambda is 3. I am multiplying both sides with minus. So minus 6 times lambda and what? Minus, so plus 4 equal to 0. Right? Now let us go to the Horner method to find the roots of this. And it is familiar to you. We have seen this in PUC, Horner's method. Okay, for finding the roots of higher degree polynomial equation. So now first raise 3 coefficient is 1. Okay. Next raise 2 coefficient is not there. Lambda square coefficient is not there, therefore 0. And lambda coefficient is minus 6 and constant is 4. Now let us keep on trying which one will satisfy us. Now let us try for 1. Okay. So first 0, 1 plus 0, 1. 1 ones are 1, 0 plus 1, 1. And 1 ones are 1, it is minus 5 and minus 5. So it is not satisfying, right? It is not 0. It has to be equal to 0, then only this become root. So then let us change this. I'm changing this because it is not a root. So like this you have to keep on verifying which it satisfies. Okay. Now let's try for minus 1. 1 plus 0, 1. Minus 1 into 1, minus 1. Again minus 1. Plus 1. It is minus 5. It is plus 5. And 4 plus 5. 9. Again it is not equal to 0. So again we have to change this. So like this you have to keep on search. So if you got one root, if you are getting one root, that is enough. Remaining two roots you can obtain by using minus b plus or minus b square minus 4ac formula. Our goal is to find one root until you have to study. Let us try for 2. 1 plus 0 1, 2 1s are 2, and 0 plus 2 is 2, 2 to the 4, so it is minus 2, minus 2 to the minus 4, and 0. Perfectly alright. Satisfying. Therefore, this 2 become a root. So therefore, this can be written as, so therefore, lambda power 3 minus 6 times lambda plus 4 is equals to, since 2 is a root, right? So therefore, lambda minus 2 I can write because 2 is a root. And that means I am factorizing this cubic equation like this. Okay, I am factorizing this. I am splitting this. Okay, lambda minus 2 into, and here second degree polynomial, this is lambda square coefficient. So lambda square into 1 is lambda square. This is lambda coefficient, 2 into lambda plus 2 into lambda, and constant is minus 2. So rewrite like this. And how to get remaining two roots? Simply by using formula minus b plus or minus b square minus 4ac by 2a. B square minus 4 times ac by twice a. Yeah. Now let us plug in back all the unknowns. So minus b. So it is minus b in this. So in this second degree I am looking. So in this only I am looking. Okay. I am finding two roots here. Already one root we got, there is 2. Yeah. So minus b, so minus 2 plus or minus square root of b square. So 4 minus 4ac. So plus 4 to the 8. 4 to the 8, right? Isn't it? 4 to the 8. And by twice the a, so 2. So finally it will be, what is it? So minus 2, 12. So 4 3 is a 12, therefore 2 will comes out. 2 into root 3 I can write by 2 plus or minus. So therefore clearly I can say that, so therefore eigenvalues are what are eigenvalues now? So lambda 1 is 2 because here look at lambda minus 2, right? Next lambda 2 is second eigenvalue. So these are eigenvalues of which matrix? A, right? Eigenvalues, let me write clearly, eigenvalues of A are, okay, we found eigenvalues of A, but this is not our question. Our question is eigenvalues of A inverse. Yeah. So now lambda 2, so 2 and 1 times it will getting it to cancel, so minus 1 plus root 3. Okay, and what is lambda 3? Last eigenvalue minus 1 minus root 3. So these are the eigenvalues of A. Then conclusion is, so therefore eigenvalues of, okay, eigenvalues of A inverse, eigenvalues of A inverse are 1 over lambda 1, sir, because reciprocal of those eigenvalues, right, based on the property. Now what is that? 1 over lambda 1 is 2, so 1 over 2, first eigenvalue. And next second eigenvalue 1 over lambda 2, right, reciprocals. So 1 over minus 1 plus root 3. Okay, and third eigenvalue 1 over lambda 3 is equals to 1 over minus 1 minus root 3. Okay, so this is a way of finding eigenvalues of inverse of the matrix. So which is 1 over minus 1 minus root 3. That's it. So therefore, so this is first eigenvalue. This is a second eigenvalue. Okay, and this is a third eigenvalue of the inverse of the matrix. Okay, inverse of the matrix. That's it. So therefore, characteristic roots of A inverse are simply 1 by 2, 1 by minus 1 plus root 3, 1 by minus 1 minus root 3. These three are the eigenvalues of A inverse. Clear? And you can cross verify whether these three are eigenvalues of A or not. How to cross verify? Simply by the properties again. What is the sum of the eigenvalues indirectly? Trace, right? But trace is here is 0. So let us compute now. So 2 plus minus 1 plus root 3 plus minus 1 minus root 3. So minus root 3 plus root 3 cancel out. Minus 1 is minus 2. Minus 2 plus 2 0. Look at sum of these three eigenvalues becoming 0. Verify. So, and similarly you can find the debt. Debt should be equivalent to product of these three eigenvalues. We can cross verify whether these three are the exact eigenvalues or not. Okay, clear? Yeah, next one, let us go to the problem number 2. If the eigenvalues are characteristic values of a 2 by 2 matrix are 2 and 1, it is given already 2 and 1, no need to compute. Then find the eigenvalues of 3 times A and A square and A to the power of 2021, A inverse and adjacent of matrix A. Okay, now let us compute. So sometimes eigenvalues are directly given, so no need to compute now here for the old matrix. Here the old matrix is A. So therefore, lambda 1 is equals to 2, comma, lambda 1 is equal to 1 are the eigenvalues of A. This is given. Then based on that first question, what do we want? Eigenvalues of 3A. Okay. So we want eigenvalues of 3A. Eigenvalues of 3 times A. So now based on the property, how to get eigenvalues of 3A? 3 is like K. 3 is like K. So K times A. So what are the eigenvalues of K times A? K times the old eigenvalues. So therefore, by the property, if lambda 1 comma lambda 2 are the eigenvalues of A or the eigenvalues of A, then yes, K times lambda 1 comma K times lambda 2 are the eigenvalues of K times A. This is a property. Why I have taken only 2 eigenvalues? Because here the problem is 2 by 2 matrix. If it is 3 by 3 matrix, you write the property like this. By the property, if lambda 1, lambda 2, lambda 3 are the eigenvalues of A, then K times lambda 1, K times lambda 2 are the eigenvalues of K times lambda 3 are the eigenvalues of K times A. Like that you can write, you can modify the property. So therefore, by this property, so therefore directly answer without computations. So therefore, eigenvalues of 3 times A are 3 times lambda 1 and 3 times lambda 2. That's it, over. So then compute what are the 3 times lambda 1, 3 times lambda 2. So what is 3 times lambda 1? 3 into lambda 1. Lambda 1 how much? 2. So 6. This is the first eigenvalue. And 3 times lambda 2 how much? So lambda 2 is 1. So 3 times 1, which is 3. So therefore, final conclusion is therefore 6 comma 3 are the eigenvalues of matrix 3 times A. So this is the final conclusion. 6 comma 3 are the eigenvalues of 3. So like this we can proceed. Similarly, second one, yeah, what is second one? Eigenvalues of A square. How to get this? Eigenvalues of A square. How to get eigenvalues of A square? Again same, by the property, See here, no need to proceed like this compulsory. See, for example, first question, first to compute what is 3 times A, you will get a new matrix and find the eigenvalues of that matrix by general method. What is general method? A minus lambda equal to 0, characteristic equation, right? You solve it, you will get the roots. So that is a general procedure. So instead of again solving, directly we are applying this property, so we are saving time. Okay. By that property, directly we can get the new eigenvalues for the modified matrix A. What is the modified matrix? 3A. Second problem, by the property, if lambda 1 comma lambda 2 or the eigenvalues of A or the eigenvalues of A, then lambda 1 power k comma lambda 2 power k are the eigenvalues of A power k. Okay, what is k? K is positive integer z plus. Okay, z plus. So by this property, I can attack this problem. So now I want what is eigenvalues of A square. So therefore, eigenvalues of A square, values of A square are yes lambda 1 power 2 comma lambda 2 power 2. That's it. Simply you have to square it because A square eigenvalues we want. So therefore, let's find what are those. So which are nothing but what is lambda 1 square? What is lambda 1 here? Lambda 1 is 2, so 2 square, which is 4, comma lambda 1 square. What lambda 2 square? What is lambda 2? 1. 1 square, which is nothing but 1. So therefore, conclusion is 4 comma 1 are the eigenvalues of A square. Okay. Therefore, 4 comma 1 are the eigenvalues of A square. That's it. So this is the conclusion. Understood? Next one, similarly, what do you want? Third question, A to the power 2021. Same. Just now I did A square, right? Instead of power 2, you write power 2021. Then what are the eigenvalues of A power 2021? So directly I am writing answer. So third one. So lambda 1 to the power of 2021, which is nothing but 2 to the power of 2021, comma, and lambda 2, which is nothing but 1, so power 2021, so 1 to the power of 2021 are eigenvalues of A power 2021. That's it, A power 2021. Okay, you write clearly, just already have done, so directly I am writing. So A to the power of 2021, right? Similarly, fourth one. What is the fourth one? Come to the fourth question. Eigenvalues of A inverse. How to get A inverse? So fourth one. Eigenvalues of A inverse. Eigenvalues of A inverse. Okay. How to get this? If lambda 1 comma lambda 2 are the eigenvalues of A, then 1 over lambda 1 comma 1 over lambda 2 are the eigenvalues of eigenvalues of A inverse. Eigenvalues of A inverse if A is non-singular. Is it required A is non-singular? Yes, it is compulsory required. Why? Because if A is a singular matrix, if A is a singular matrix means what? Determinant should be 0. Okay, let me write here. Singular matrix means determinant should be 0. That means what? What is the determinant actually? Product of eigenvalues, right? So for example, lambda 1 into lambda 2. So this becomes 0 if it is a singular matrix. If it is a singular matrix, then it compulsory 0, right? Singular matrix. Then compulsory any one of the eigenvalue compulsory 0. Both can be 0 or any one of the eigenvalue can be 0. Like if lambda 1 is 0, lambda 2 can be any number. Or lambda 1 can be any number and lambda 2 is 0. Or both can be 0. In all the cases, at least one eigenvalue becoming 0. If any one of the eigenvalue becoming 0, that means that is happens in singular matrix only. Then reciprocals are not possible. Okay. First of all, A is singular, then A inverse does not exist first of all. A is a singular. So for singular matrix, this property does not work out. Okay. So compulsory any one of the eigenvalue must be 0, then 1 over 0 becomes infinity, undefined. Eigenvalues becomes undefined for that. So that is the importance of non-singular here. Okay. Then, yeah. Come here. So therefore, 1 over lambda 1 I want. So what is lambda 1 there? 1 over 2, comma 1 over lambda 2 is nothing but 1 over 1 are the eigenvalues of A. That's it. Simply we have to do reciprocals. Okay. Similarly, fifth one, we want eigenvalues of adjacency matrix, right? Fifth one. Yeah. So eigenvalues of eigenvalues of eigenvalues of adjacency matrix. I hope you know what is meant by adjacency matrix. Yeah, what is that? Lambda 1 comma lambda 2 are the eigenvalues of eigenvalues of A, values of A, then determinant of A divided by lambda 1 comma determinant of A divided by lambda 2 are the eigenvalues of the new matrix adjacency, the matrix A. Okay, so therefore yeah, so what is the new eigenvalues for the adjacent matrix? dA by lambda 1 is equals to, what is determinant of A? Product of the eigenvalues. What are the product of eigenvalues? 2 comma 1 are the eigenvalues, therefore 2 into 1 2 divided by first eigenvalue is 2 by 2 comma, and next the determinant of A divided by lambda 2. Okay, what is det? Det is again 2 and lambda 2 is 1. Okay, this is nothing but 2 and this is nothing but 1. Okay, and these are the eigenvalues for the matrix, adjacent matrix. So therefore 1 comma 2 are the eigenvalues of the adjacent matrix A. So this is the conclusion of this. How to cross verify this? How to cross verify? Simply, already matrix is given to you. This is a matrix. Let me cross verify this one here itself. Okay, let me do this. Now let us look at the first one. First one cross verify. 3A. How to get 3A? 3 times A. So if you don't want to apply the properties, you can proceed like this. 3 times A. So 3 times. What is the matrix A now? 5 minus 3. 5 minus 3. and 4 minus 2. 4 minus 2. What do you get inside? So 15, 3 5 is a 15, minus 9, and 3 4 is a 12, minus 6. So now for this matrix you have to find the eigen values. So how to get that? So assume this matrix is some B. Okay, I'm renaming. So now B minus lambda into I, or simply you can write here 3a minus lambda I, you can write, no problem. So then accordingly directly I'm writing, so 15 minus lambda, 15 minus lambda, minus 9, 12, okay, and here minus 6 minus lambda, get equal to 0. Then simplify this. So 15 minus lambda, 15 minus lambda into, or you can cross verify, no problem, minus 6 minus lambda, and plus 108. 12 9 is a 108, equal to 0. Okay. And this one lambda square, next plus 6 lambda minus 15 lambda minus 9 lambda, okay, and minus 90 plus 108 equal to 0. And this is nothing but lambda square and minus 9 lambda, okay, and 10 18 plus 18 equal to 0. So now factorize this. How to get factorizing? So if you do sum, you will get minus 9. If you multiply, you will get minus 9. If you do addition, you will get 18. Like that, you can cross verify. Or simply by this matrix only. So you got new matrix P. So 15 minus 6. How much? Trace of this matrix 9, isn't it? Trace is 9. So the new eigenvalues 6 comma 3 are the new eigenvalues. Look at trace is 9 again. Some of the eigenvalues are 9, trace is 9. And similarly, you find the determinant 15 into minus 6 plus 12 into 9. So that determinant will be equal to 6 into 3. So like that you can cross verify. I can factorize this, you get the eigenvalues are 6 and 3. So similarly, here this I can write lambda square. I can write minus 6 lambda minus 3 lambda, right? Minus 3 lambda plus 18 equal to 0. Equal to 0. Then factorize this. Here you take lambda common. Let me write here. If you take lambda common, what will you get? Lambda minus 6. Okay. And next minus 3 common. Lambda minus 6. So equal to 0. So finally what will you get? Lambda minus 6 into lambda minus 3 equal to 0. Okay. Therefore, what are the eigenvalues now? 3 and 6. So this is a general approach without applying any property. Look at this much we have to struggle. But here directly, by if you know the property, directly simply multiply with 3 of the old eigenvalues. Old eigenvalues are 2 and 1, multiply with 3. 3 to the 6, 3 1 to 3. 6 comma 3 are the eigenvalues. Look at within a fraction of seconds, you are able to give the answer. But here is not like that. You have to do the computations like this. So similarly, a square also same by computations. A already given. Then compute what is a square. Similarly, but this one a power 2021. This is very difficult. How to find a power 2021? That many times you have to multiply this matrix. It will take a lot of time if you don't apply property. So that is the power of properties. But if you apply the properties directly, 2 power 2021, comma 1 power 2021 are the eigenvalues. Simply. Understood the power of the properties. Okay. Yeah. Next. Problem number 3. If the eigenvalues or characteristic values of A, 3 by 3 matrix I have taken, 0, 3, 15. This one already I have taken the matrix. Okay. Anyway, eigenvalues are already given. Then find the eigenvalues of A cube, A transpose, and A inverse. Okay. If lambda 1 is equal to 3 or 0, and lambda 2 is equal to 3, and lambda 3 is equal to 15 for the eigenvalues. are the eigenvalues of the old matrix A. Then first one is we want eigenvalues of A cube. Therefore, eigenvalues of A cube. Directly I am writing, but you write clearly. You write the property. After that, you write. Okay. Then what is that? Lambda 1 cube is nothing but 0 cube, which is nothing but 0. Next, lambda 2 cube. You have to do power 3. So 3 power 3. Okay. And next one, lambda 3 power 3 is nothing but 15 is a lambda 3 and its power 3. So therefore, conclusion is, what is the conclusion? Therefore, 0, comma, 3 power 3, comma, 15 power 3 are the eigenvalues of A cube. A cube is a new matrix. For this matrix, these are the eigenvalues. Clear? Next, similarly, second one, A transpose. So eigenvalues of A transpose. Eigenvalues of A transpose. Again, by the property, what is the property? Eigenvalues of A and A transpose does not change. Okay. So eigenvalues of A and A transpose are same. So therefore, eigenvalues of, if you are getting doubt, you can try in a general method. Eigenvalues of A transpose are, what are the eigenvalues of A transpose? Same eigenvalues only, 0, 3, 15. If you are getting doubt, find what is A transpose, you will get a new matrix and find out eigenvalues of that A transpose matrix. In general method you can calculate. I mean to say is you find out what is characteristic equation, cubic characteristic equation will get, cubic polynomial equation. Solve it, you will get 3 roots. The 3 roots are nothing but this one, 0, 3, 15. Okay. And look at the last one. What are the eigenvalues of A inverse? Eigenvalues of A inverse. Eigenvalues of A inverse. What is the answer? It does not exist. How? Why? Because the matrix A is singular matrix. How it is singular matrix? Since A is singular. A is singular. A is singular. Or simply instead of writing like this directly, let me conclude A is singular. Okay. Since what is determinant of A? Determinant of A is nothing but product of eigenvalues, lambda 1 into lambda 2 into lambda 3. So these are the det A. So what is that? Lambda 1 0 into lambda 2 3 into 15. Answer is not 45, 0, because 0 into there, right? So det A is equal to 0, therefore A is singular matrix. So once it is singular matrix, then inverse does not exist. Singular matrix. So therefore A inverse does not exist. A inverse does not exist. So therefore matrix itself is does not existing, then how can you find eigenvalues? So therefore eigenvalues also does not exist. So therefore eigenvalues does not exist. Does not exist. So this is the final conclusion. Understood? So if you know the eigenvalues, you can tell what kind of matrix it is. So here the eigenvalues are 0 to 15. So clearly this matrix is singular matrix. If you're getting doubt, you can find the determinant. Yeah, let me cross verify this. Look at now. Just this cross verification is not required. Just let us cross verify. Yeah, first find out what is the det of this. So 8 into, yes, 8 into 7 3 is 21 minus 4 4 is 16. Next, minus of minus plus 6 into minus 18 minus 18 and plus 8 minus of minus plus, right? Next plus 2 into 24 minus 14. Find out. So 21 minus 16, how much? 5. 5 8s are 40. Minus 10, so minus 60. And 10 to the 20 plus 20. Look at 40 minus 60 minus 20 plus 20 0. That is 0. That's why this is a singular matrix. Understood now? So without finding this directly, you multiply the eigenvalues, you will get the determinant of this matrix. So this is about problem number 3. Next problem number 4. So find the characteristic polynomial of a 2 by 2 matrix by the help of eigenvalues. Only by the help of eigenvalues we have to compute. Okay. So solution. In general, how to get characteristic polynomial? So in general, characteristic polynomial of the matrix A. The matrix A is determinant of A minus lambda I simply. This is a characteristic polynomial. But I don't want by these calculations. By the help of eigenvalues, you have to find what is a characteristic polynomial. Okay. So therefore, what we have to do is, so let lambda 1 comma lambda 2 are the eigenvalues. Of the matrix A is, what is that? 2 0 0 3. Okay. So these are the eigenvalues of A. Then clearly, what I can say, therefore, conclusion, lambda 1 plus lambda 2 is equal to how much? Sum of the eigenvalues are nothing but trace, 2 plus 3 is nothing but 5. So this information I had. Next, product of the eigenvalues, lambda 1 into lambda 2 is nothing but determinant of A. What is the determinant of A here? 6. So these two values you had with you. So based on these values, now you have to construct what is a characteristic polynomial. See, remember, I am not computing what are eigenvalues. How to get eigenvalues? Again, you have to go this. Go to characteristic polynomial, which is A minus lambda I. Then equate this one equal to 0. You will get characteristic equation and solve it. You will get eigenvalues. Indirectly, you are using this formula. But I don't want to use this formula. Simply by the help of eigenvalues only, I want to find the characteristic polynomial. So I am not finding by using this formula. Now sum of eigenvalues is 5 and product of eigenvalues is 6. So therefore, general form of characteristic polynomial, okay, characteristic polynomial of a 2 by 2 matrix. Because here the problem is of 2 by 2 matrix is A naught lambda square, because it is 2 by 2 matrix characteristic polynomial, plus A1 lambda plus A2 equal to 0. This is general form. What about A naught, A1, A2? That will be decided later. Okay. So this is a general formula. Assume this is number 1. Okay. And this one, and this is number 2, and this is number 3. Okay. So clearly, sum of the eigenvalues are 5 and product is 6. So directly, Since sum of the eigenvalues, sum of the eigenvalues is equal to lambda 1 plus lambda 2 is nothing but what? The formula minus a1 by a naught, right? Look at from 1 minus a1 by a naught, sum of the eigenvalues is nothing but how much? 5. So indirectly minus a1 by a naught value is given to us. Okay. Now, and so from this I can say that what is a1 value? a1 value is minus 5 a naught. Keep this aside. Next, product of eigenvalues. Product of eigenvalues. Product of eigenvalues is equals to product of eigenvalues is equals to lambda 1 into lambda 2 product. Now what is that? a2 by a naught. Okay, a2 by a naught. Which is nothing but how much? Product is 6. Indirectly from here I can get what is a2 value? a2 value is nothing but what is a2 value? a2 is nothing but 6 times a1. 6 times a naught. Now take the equation number 1, then modify this. So 1 implies, then plug in back all the values. So a naught lambda square plus, what is a1 value from here? From here a1 value is minus 5 a naught into lambda plus a2 value 6 a naught equal to 0. So finally you take a naught is out, lambda square minus 5 times lambda plus 6 equal to 0. And here it's like a product of two values a and b. A into b equal to 0. Compulsory either a is 0 or b is 0. For example, if a is not equal to 0, this is not equal to 0, then b must be 0. This b compulsory equal to 0. Then only product of these two must be 0. So same here, look at so here you look at what is given. This is one number and this entire thing is 1. Okay. Now product of these two is equal to 0, but here a not equal to 0. Why? Because look at this one. If a naught is equal to 0, look at this. Look at this one here, the relation. If a naught is equal to 0, what happens? Minus a1 by 0 will become infinity, but you are getting 5. So a naught compulsory should not be equal to 0. That's why a naught is not equal to 0 here. So here a naught is not equal to 0. So therefore, what will be equal to 0? Lambda square minus 5 lambda plus 6 equal to 0. That's it. So this is a characteristic polynomial. If you want, you can cross verify. Compute by using this formula. You will get a lambda square minus 5 lambda plus 6. Okay. Or you can do like this also. Second method. How to find by second method? So same again. Since it is a diagonal matrix, right? Since it is a diagonal matrix, the eigenvalues are nothing but diagonal entries only. These entries are nothing but eigenvalues only. So first eigenvalue is 2, second eigenvalue is 3. So directly lambda 1 is 2, lambda 2 is 3. Take. So therefore since it is diagonal, since A is diagonal matrix, or simply A is both upper and lower triangular matrix, right? Every diagonal matrix is both upper triangular matrix and lower triangular matrix. So every triangular matrix having the diagonal entries as a characteristic roots or eigenvalues. Eigenvalues are nothing but diagonal entries only for every triangular matrix. So these are also one of the triangular matrix. Therefore, diagonal entries are nothing but the eigenvalues. So 2 and 3 are the eigenvalues. Since A is diagonal, okay, A is diagonal, A is diagonal. So therefore, eigenvalues are eigenvalues are 2 comma 3, 2 comma 3. Okay, then again same story. What is this a naught? So again same, again minus a1 by a naught. Sum of the eigenvalues is 2 plus 3 5, and product of the eigenvalue is 6. Like that you can proceed. Or simply here we derived one formula, right? What is that formula? Minus 1 whole to the power of n. So here 2, since it is 2 by 2 matrix, lambda square. Next plus minus 1 whole to the power of 1 lambda into trace of the matrix e1 1 plus a2 2. So remember, this also I got the formula. And last one plus some constant, let's call it. So here minus 1 whole to the power of 0, right? Last one. So this one is minus 1 whole to the power of 0, minus 1 whole to the power of 0 into some constant is equal to 0. And now here, what is a1 1 plus a2 2? Trace is nothing but 5 here, sum of the eigenvalues. So here you replace 5. Okay, and this is minus 5 lambda. Look at lambda square minus 5 lambda. And minus 1 whole power of 0 is 1. And c, what is c actually? Substitute lambda is 0 in this, you will get determinant of a. Determinant of a is nothing but last constant c. So what is c value now? 6. Substitute here, c value 6. So like this also you can get it. Understood? So this is about characteristic polynomial without using the formula determinant of a minus lambda a. And this technique work out if it is a 2 by 2 matrix. If it is a 3 by 3 matrix, this technique will not work out. Why? Because these two entries we are finding perfectly, lambda coefficient and constant. If it is a 3 by 3, if it is a 3 by 3, we'll get some a naught into lambda cube, okay, plus a1 into lambda square, right, and plus some a2 into lambda, a2 into lambda, plus some constant a3. So a3 here, a3 and a1, this you can find no problem by the same concept, but you cannot find what is a3. Is nothing but product of 2 eigenvalues, right? Product of 2 eigenvalues. For example, if alpha beta gamma are the roots, then what is the sum of the roots? Alpha plus beta plus gamma. That is nothing but minus a1 by a0. What is 2 products roots? Alpha into beta, alpha into gamma plus beta into gamma is equal to a2 by a0. So that we cannot find here clearly. So this constant we cannot find if it is a 3 by 3 matrix. Okay. And with this I will stop. I will continue in next class.